Oh, yeah, I see. Okay. Oh, right. I'm supposed to. Okay. Okie dokes. Did I start a recording? Yes, I did. Okay, about a minute ago. Oh my goodness. All right. It is Thursday, April 23rd, at 11 a.m. Welcome back. I just got an email from somebody on campus about other options for joining WebEx, so I will try to sort through that email and test something and then send out an email when I get a chance. I know I'm behind in grading and I'm really sorry about that. Last weekend, the major one was grading this calculus exam. So this weekend, there's no major assignment grading other than just catching up. So my hope is that you'll just get like every half day or so you'll get this thing is graded and that thing is graded. That's the big goal for this weekend. Well, really starting tomorrow, to be honest with you. A couple notes here. Homework 10 due today, Thursday. Homework 11, I just posted like 3 minutes ago, 5 minutes ago, something like that. So please take a look. There are certainly questions in homework 11 that deal with some of the newer ish things that we've been working on, like functions and cardinality and induction and this kind of thing. There are also, though, questions that really take you back to kind of just friendly reminders. I think it's how to use and prove for all statements and things about relations. So some kind of older things are there. I hope what that does is it kind of eases a little bit of the burden, and also the specific types of problems that are being picked as a bit of a review are sort of ramping up towards the final exam and just kind of things that people tend to forget a little bit about. So there are some review-ish type questions in there. So I hope that creates a good opportunity to revisit things. I mean, everything all fits together, but maybe having some things that don't deal with some of our newest stuff might be helpful. There is an exam set for next Thursday. Obviously, take-home exam. I have to work on some of the details of some things, but in terms of format, you kind of saw what I'd like to do, though, is just have you directly upload a PDF into Gradescope, just like for the take-home quizzes. I need to get some practice questions out and available, and so yeah, those are some of the things that will kind of occupy me through today. But by tomorrow morning, you should have hopefully plenty of practice problems and the sort. Okay, I think that'll work for announcements. We don't have a whole lot I want to say left for induction. I do want to try this kind of unique problem that I learned of once myself when I was an undergrad. Because I think sometimes what happens is, oh, induction, it's just on these boring number related problems. But, here's something kind of just fun. It's like, I hope that this theorem that we're about to prove together is accessible, but it's kind of different. So it's just don't stress about it too much. But I certainly ask questions if you have any questions related to this one. So for all n greater than 0 integer, it could have been phrased n greater than or equal to 1 integer, after removing a 1 by 1 square from a 2 to the n by 2 to the n chessboard, the remaining squares. So how many squares are there? Let's just include that for clarity. So first of all, if the height is 2 to the n and the width is 2 to the n, then the total number of squares should be 2 to the n times 2 to the n. But we just talked about removing a square. So the remaining 2 to the n times 2 to the n minus 1 squares can be tiled with the following shape. So it looks like, sort of looks like a Tetris piece. So like that. So it's like 3 squares that form the shape a little bit of an L. And this piece, for the sake of this problem, can be rotated around if you want. Okay, I know this is a little strange. Just what I mean by 2 to the n by 2 to the n chessboard is, like, think about, when you play chess or checkers, you play on an 8 by 8 board. So in that case, n is equal to 3, right? So n is 3, so you have 2 to the third, or you have 8 by 8. There's normally a total of 64 then squares where pieces can be on a chessboard. But if you take your 64 spots and you just remove one square, as if chess pieces can't exist on one of the squares, then there'd be there's 63 spots left. So for a proof of this, it is phrased as is for all n positive integers. So we're going to do a proof by induction. So with a base case first. So I'd like to prove that this happens on a 2 to the 1 by 2 to the 1 chessboard. So in other words, what we want to prove, or want to show, is after removing... Actually, I want to clarify here, not just a 1 by 1 square, any. So after removing any 1 by 1 square from a 2 to the 1 by 2 to the 1 chessboard, the remaining can be tiled with this shape, like that. So the 2 to the 1 by 2 to the 1 chessboard, right, looks like, so height of 2 and a width of 2, so that board here looks like this, right? 2 spaces across, 2 spaces down, so a total of 4 spaces. So if this is supposed to be true after removing any one of these 4 individual squares, there's actually 4 cases. So case 1, what if you remove the upper left square? So if this square, let me kind of erase that by smudging this like this, get rid of that one upper left corner. If that's gone, then the tile piece, this piece that's up there, you just need to rotate it, and it lives right here. In case 2, maybe, the removed piece wasn't the upper left corner, maybe it was the upper right corner. And so then the tile piece can exist in that spot right there. You just have to rotate it. And there's 2 more cases, but we will kind of leave those be if that's okay. I think doing 2 out of the 4 cases, are we all right with that? The other, these cases, the case 3 and case 4 are similar. So these 4 cases will take care of the base case here. But now for the inductive step, right? So there's this. So at the same sort of indentation level as a base case, not that I'm worried about how you're indenting, but I'm just trying to point out for the argument here, the inductive step. So what we need to do is we need to assume, let's let k be an arbitrary positive integer. And we need to assume that at 2 to the k times 2 to the k by 2 to the k board can be tiled by this shape after removing Any one square. Okay, that's the, if P of k, then P of k plus 1. So that's our P of k assumption, or rather our inductive hypothesis. What we want to show is that a 2 to the k plus 1 by 2 to the k plus 1 board can be tiled by this shape, by tiles that look like this. You have many copies of that same tile after removing any one square. Are we okay with that as a setup for what's going on here? Just to scroll back up, make sure we're all here with this. We're doing this by induction. The statement we're proving is for all positive integers n, after removing a single square, any square you want, from a 2 to the n by 2 to the n chessboard, the remaining spaces, so it's the 2 to the n times 2 to the n minus 1 squares, can be tiled with this. And we did a base case, and so now what we're doing is working on the inductive step. So fixing a positive integer k that we don't get to control, the reader picks. And so then we are assuming this, that n, after removing any 1 by 1 square, and that's what this phrase is here, right? So after removing any one square, this 2 to the k by 2 to the k board can be tiled by a piece that looks like this. And what we want to show is that a 2 to the k plus 1 by 2 to the k plus 1 board can be tiled by this tile shape after removing any one square. So what I'm going to do is draw this huge 2 to the k plus 1 by 2 to the k plus 1 board. Right? So the number of tiles going down this way, I mean, not that I don't want to draw all these individually like this because we don't even know what k is, so this is a bit of a cartoon. But there's 2 to the k plus 1 spaces going down, and then there's 2 to the k plus 1 squares going across. So in total, the number of squares is this times that. But here's the thing then, the fortunate thing is that the number of spaces across is a power of 2. So if we divide this in half, this will work out because these numbers are even. So maybe I'll label over here, the number of spaces going down this way should be half of this number, right? Or in other words, it should be the number of spaces here should be 2 to the k plus 1 half, so divide by 2, and that ends up being 2 to the k. So this is 2 to the k, there's another 2 to the k right there. This number of squares across here is, for the same reason, 2 to the k, and we have here 2 to the k. Okay, so what we want to do here is take this 2 to the k plus 1 by 2 to the k plus 1 board, and we want to remove any one square, and then tile using this shape right there. So to do this, I normally ask in class who wants to be a brave volunteer and pick a square, but I'm going to just try this gimmicky thing. So I'm going to open a poll, and y'all should now be able to vote. And once you make a selection, you may need to click on a submit button in the corner. So we'll just kind of go with like any square. So does the little square come from the upper left block? There's a lot of squares over here. Does it come from one of the squares over here? That's what I want to try to ascertain. I've got 4 voting out of oh, right, because I'm 2 of the people. Oh my goodness. All right, close the poll. Let's see poll results. I've got 1 voting for the upper right, 1 voting for the lower left, and 2 voting for the lower right. So somewhere in this lower right, there's still lots of squares here. I'm just going to pick a spot. Like, how about within here, there's 2 to the k squares across, 2 to the k squares here, so a total of 2 to the k times 2 to the k. And of those, I'm just going to pick like Yeah, there's a little square right there. So I'm going to remove that square. So having removed the square, let's go back. I'm going to copy paste this inductive hypothesis, right? We assumed this. I'm going to paste this down here so that we can see it a little better. So our assumption, our inductive hypothesis, this is the thing that we get to use, was that after removing any one square from a 2 to the k by 2 to the k board, that we can tile using this shape. I mean any square, right? And so here in this block, let me maybe shade this in red. Over here, we do have one single square removed, and the point was it was any one square removed. This part can be tiled, check. That part's done. But then you might say, well, okay, so that's a 2 to the k by 2 to the k board that we can tile by the inductive hypothesis. But what do we do in these spaces over here? Well, it's convenient that just in the tiny, tiny little corner right here, I'm going to draw one copy of that tile. That L-shaped tile right there. This tile is using up, it's a 3 square tile and it's using up one little square from each of these big blocks. And remember, the assumption was that after removing any square, I mean any square from a 2 by 2 2 to the k by 2 to the k board, you can tile the rest. So in this upper left block, now that one square being used by a tile already, let's consider it removed. And so then this part can be tiled. And over here in this upper right block, one square, let's consider one square being removed because we already have a tile occupying the tiny lower left corner there. And so this part, check, can be tiled. And same deal, one square was removed in the lower left block. It was namely this tiny, tiny little square in the upper right block. And so that can be tiled as well. And so overall, with no overlapping, we were able to tile this thing. It's kind of a strange proof, so I'll just see if we have any thoughts or questions or confusions. I mean, it's just kind of a fun, just something a little different, really, is what this is about. So, any thoughts, reactions, questions, things that can be cleared up?
Could you go over just like I don't, the last like minute
Yeah,
of like
sure,
why it
absolutely.
all ties together?
Yeah. So, okay, so, and then let's just go back, and it goes back to just the statement, and I should have said it better in the beginning, so I apologize about that. But the statement here is no matter which positive integer, n is used as the exponent, right? So you have a 2 to the n by 2 to the n chessboard. And then if you remove any square, and I think the emphasis I want to make is you remove any one little 1 by 1 square, then the remaining, looking at all the remaining spaces, using a shape that looks like this, the shape that ends up using 3 individual 1 by 1 squares that are glued together in this L shape that's in the blue circle here, using that shape without any overlapping, you can tile the rest of the board. So every spot, other than the one removed spot, is accounted for and covered once and only once by a shape that ends up this L shape that uses 3 squares at a time. So the base case was to remove, it's a 2 by 2 board because the exponent is 1, so 2 to the 1 by 2 to the 1. And of the 4 squares, if you just remove any one square, the remaining 3 pieces actually already form that L shape. But the key thing about this inductive step was the assumption, again, it goes back to this any, right? So after removing any one square, from a 2 to the k by 2 to the k board, you can tile using this shape. So the thing we want to prove, right, it's if p of k, then p of k plus 1. So what's p of k plus 1 is right here. It's if you remove any one square, from a 2 to the k plus 1 by 2 to the k plus 1 board, you can tile using this shape. So here, this big, huge square, it's our cartoon of a 2 to the k plus 1 by 2 to the k plus 1 board. And if you can chop this, into, you just cut it in half each way, you get these 4 window panes, and each of these 4 regions here ends up being let me actually remove this to the question was to repeat the argument. So let me try to do a a decent-ish job of this. The whole point is if you remove one little tiny square anywhere in whether it's from this part, this part, this part, or that part, any one of these four parts, we should be able to tile the remaining. So as far as picking where's that little square could have been picked here, or it could have been picked there. I mean, here, it could have been there. Here, anywhere in this lower left block. Oh, whoops. Could have been where the square was, but I just kind of did that WebEx poll, and the majority vote was to remove the little square from this region, because there's really technically four cases, but I just figured that if I gave you all the somewhat random choice of you pick which of these four big blocks the little one by one square is removed from, you could then probably do the other three cases in a similar way. So if we remove this one little square, then by the inductive hypothesis, this 2 by 2 block here has one removed square, and we can tile the rest, right? Because the inductive hypothesis down here, the assumption was that a 2 by 2 to the k by 2 to the k, which is what that's how the size of this is, after removing any one square, like for instance including that one square, can be tiled. And then these other three parts here, I'll shade them this way right now. Those are 2 to the k by 2 to the k's, but we can't tile them using this because the assumption was you can only tile using this when you remove a square. So what I'm going to do is I will insert one tile piece that's just right in the corner right over here, right? Because we do need to tile all spaces except for this one removed square. So this tile, it's part of the tiling of this big shape. But also, if that tile is there, then within talking about tiling this region, let's say that that's the removed square. Let's see. And then the question that comes by chat, the tile in the middle is from trying to tile the entire big square. Yes, no, yeah, thank you. I should have said that. That's what the functional role of this tile here is. So that, I've drawn it in red this time. I forget already what color I did it last time. But that little L shape there, it's part of the bigger tiling of the big region, but it also functionally serves a role of, when just discussing this upper right region, that's this 3 square tile piece over here. Let's call that the one removed square, because remember, if you remove any one square from a 2 to the k by 2 to the k, you can tile the remaining. Does that sort of work? Does that kind of help?
Yeah, that definitely makes sense now. Thank you.
And it's a strange one. I'm not expecting people to recreate this. I mean, it's kind of fun to understand this proof. Don't get me wrong, but don't stress out over it. I think part of this is to say, proof by induction, kind of, it's just something just a little different and fun. It's just kind of unique, and it's just kind of neat that you can literally take this. I'm convinced. Like, I don't need anything other than the argument here to, like, if somebody made like a 2 to the 2 to the 8th is what? Is that 256? If somebody made a chessboard that has 256 rows and 256 columns, and then just removed one square, and then gave me all these little Tetris pieces that look like this, I know, due to the proof that my pen just died. Oh, no, come on. Okay, I know that due to the proof we just did, just remove one square out of this, I can take, if you just give me enough paper copies of that thingy, there's a way to paste these in and cover all the remaining spaces other than the one removed square. So just something sort of funsies is all. Don't stress too much about that particular proof. What I want to do then is, I announced it right at the beginning, though I know some people had to join a little late. For this semester, what I'd like to do is, normally an exam goes up to the end of class previous Thursday, but I don't want to do that this time. I want to cut it off a little earlier. It'll create a clean break. I think it'll be more convenient for you. So this is the end of material for exam 3 next Thursday, right? So Um, Next Thursday's exam can talk about, sets, relations, functions, cardinality, and induction. We're going to close off what we're doing with chapter 5, and we're going to start chapter 6. So, chapter 6, which is it's rather different. It's on counting, will not be on exam 3. So I hope there are no objections to this. Like it's just a very different kind of topic. It takes a little getting used to. People don't find it too bad of a topic overall. I maintain the hardest things we do. This cardinality thing was that was cardinality and functions tends to be, I think, what people say is the hardest. I'm not saying that this chapter is all a walk in the park, but it's way nicer overall once you get used to what's going on. But I just think it would be sort of it would cause an unnecessary amount of stress to you to like include this really different kind of topic, if you will. Um, so um, yeah, let's leave this section that we're introducing off of exam 3, and it'll be part of upcoming homeworks instead, and on the final, if that's okay. Does that sound all right to folks? Just wanna It creates a clean break, I think, of material. I hope no one's offended by that. Um, this next, so chapter 6. Today, I mean to do just a preview of the ideas. Um, so it's an entire chapter on counting, and I know this sounds kind of silly. You're like counting, like one, two, three, and like, well, yes, sort of. And I will say that at least the first couple sections don't feel like they fit with the rest of what we've done this semester. And if that's how it feels, you probably kind of mostly what you're feeling is right. The first couple sections that we look at in the chapter are very skills oriented in a sense. They involve like the task of actually counting, and then a couple sections later, the thing the some of the things that we've looked at related to functions and so on start to make a brief appearance in a sense. So you'll see how it all fits together. But like these are different. I mean, they're advanced counting problems. They're not like counting problems I'd give to people in fourth grade or something like that, right? First of all, let's just so today I. Oh my goodness, sorry, my words. Today the goal is to just preview some of the ideas. I want to just get the juices flowing right, and then on Monday I want to spend the day kind of really solidifying the foundations and then clarifying some things and have you practice some problems and so on and so forth and clear up the usual confusions about the first day. So sometimes, what's this chapter about before we dig into section 6.1? Sometimes what happens is someone describes to you a set. Let's just name that set S right now. So there's a set, and based on somebody tells you a complete description of this set S. Like, you know based on what they said about S, what's in the set and what's not in the set. And based on the description, it's clear that S is a finite set. Comma. Oh, yeah, I should say this. In chapter 6, we only deal with finite sets. Which is kind of nice, right? We've been dealing with some infinite sets and the cardinality stuff and talking about uncountable and countable and none of this business, right? Just finite sets. In chapter 6, only finite sets. So you can tell just from how that S was described that S is a finite set, but computing exactly how many things are in S precisely, it may not be very obvious at least right away. May not be obvious. So this happens. I mean, this happens not just as some mathematical curiosity, though it happens in that sense. This is actually very applied. questions in chemistry and physics, biology, very often are formulated using this kind of format. This is if you took Stat 245 or for that matter Stat 145, when you deal with probability, you do things like how many what's the probability language of this? The outcomes, right? So like you count how many total outcomes there are, and that's the denominator of your fraction, and you count how many outcomes are desirable or count for the moment, and that's in the numerator. There's a lot of counting of cardinality of sets in probability. That's what's going on here. So if a lot of this sounds, if you've taken 245, maybe a lot of the ideas might sound familiar. So let me give you an example of what I mean by it's clear that S is a finite set, but it might not be that obvious how many things are in the set. So for instance, let A equal the set 1, 2, 3, 4. Now, I'm not talking about my A is not the S here. It's clear that A has 4 things in it. Let B be the set 5, 6, 7. So let S be the set of all functions from A to B. Now, S is a set of functions, right? Like if you have an element of capital S, that element that you have in front of you is a function. It's that function's domain is A and the codomain is B. And any function that you can think of from A to B belongs to the set S. So for example, let's just make one, right? So let f be the function from A to B, and f of all 4 inputs, whether you have 1, 2, 3, or 4. Let's just say that the output's always 7. So this describes a function. The output's always 7, and then based on this little f belongs to S. Okay, and of course you can define more functions from A to B. This is not the only function. I just chose one, but there's other functions you can define from A to B. But at some point you run out, right? If you're like, okay, give me another function. Okay, give me another function, and at some point you're done, right? There's only so many functions you can write from A to B because both A and B are finite sets. So we could ask a question like, what is cardinality of S? Or in other words, how many functions from the set A 1, 2, 3, 4 to the set B 5, 6, 7 are there? So does that I'm not asking for an answer to the question right away. I just wanted to show what a question of this type looks like. This counting type question, as we call this. You'll see this kind of phrasing a lot. How many? And I hope it's clear that there are only so many functions from A to B. At some point, if you want to write down another function, you'll notice, wait, the function I wrote down is already in my list of functions or in my set of functions. It already has the same domain and codomain and same rule. You can only come up with so many rules because the domain and codomain are finite sets here. But it might be not 100% obvious exactly how many functions there are. I mean, it is to me only because I've done this countings thing, and we will go through and make the answer to a question like this obvious by going through this chapter. Before doing another kind of brief example are we okay with what that example is trying to get at? Are we convinced that that S should be a finite set? If you're curious for the number, let me see if I can just compute this on the fly. The answer to this specific question actually ends up being 3 times 3 times 3 times 3, or 3 to the 4th power. But let's just ask, like based on this same A and B, how many surjective functions are there from set 1, 2, 3, 4 to the set 5, 6, 7? This is a harder question than, but the number should be something smaller than 3 to the fourth power, right? Because 3 to the fourth would count all of the functions from A to B, and now we're asking for just the surjective functions from A to B. So not all of the functions that you could list would be surjective, like for instance the one that's boxed up here isn't. But it's clear that the number of functions being discussed here is fewer than just above. And then of course you can ask another counting question: how many injective functions are there from the set 1, 2, 3, 4 to the set 5, 6, 7? So this, I'll go so far as to say this question is challenging, right? It's harder. This question, though, even though we have not developed any methods, this is actually an easier question, right? So any thoughts? Any contributions? How many injective functions are there from the set A to the set B? Any thoughts? Like 0? 0, right? So why is it 0? Because, well, we're only looking at injective functions. These are functions where two different outputs have to map to two different inputs have to map to different outputs. But if there's 4 things in the domain and there's only 3 things in the codomain, you're going to have this problem, this clash, right? Where you have this situation where it's unavoidable that different inputs have to map to the same output. There's just not enough outputs available for this function. So the answer to this, 0, right? For that counting question. So what I want to do then, if we're kind of okay, is I want to just kind of dig into and preview some of the ideas that we will do in a very formal and much clearer format. I just want to get your feet wet with this and talk about the product and sum rules. Okay, so question: how many bit strings are there of length 3? And so bit strings is just this kind of new phrase that we haven't actually dealt with, that I'm just kind of bringing up. So before digging too far, I'll just note I don't want to create. The main thing here is I don't want to create like a formal definition and require you to know it, in a sense of reciting a definition. So I'm just gonna, by example, 0010110 is a bit string of length 7. So what about a bit string of length 3 then? Well, I would like to sort of draw a cartoon and say that's a fill in the blank spot right there, and then here's another, and then here's a third, right? It's of length 3, so there are these 3 spots. And this first spot can be a 0 or a 1. And this second spot can be a 0 or a 1. And this third spot can be a 0 or a 1. Now, before you answer too hastily, since this first spot can be either a 0 or 1, there's 2 possibilities. And then this second spot, this middle spot, 2 possibilities. And there's nothing here. We're not saying that you can't repeat digits, or if you couldn't repeat, there's 3 spots and 2 choices per, so 2 possibilities. I will just say that there are various answers that I've heard to this question. So in answering this, sometimes people answer too hastily. They'll come up with, well, 2, So there's three spots, right? So the number three, and then two possibilities. And I've seen people say things like three times two. I've seen people instead bring up three plus two. I've seen people bring up two to the third, and I've seen people bring up three to the second. I mean, obviously, all these numbers are different, right? 6, 5, 8, 9. So, what I want you to do is take a moment and explore. Write how many, write the bit strings that you come up with. So, one of the bit strings is 000. Write out all of the bit strings of length 3 and see if you can come up with 6 of them or 5 of them or 8 of them or 9 of them. And you want to avoid, I guess, the situation where you accidentally write the same one twice, right? And then you don't want to write it on your list, so look carefully to see if you have any duplicates. You also don't want to miss any, so part of this is I would encourage you to think about how could you write down your list so that you can be very methodical. Well, here's what I think would be a very methodical approach to it is you start with 000, and you don't have to do this. I mean, it's not like my way is the right way or something like that. But I think what would be very methodical is thinking of these bits as like, the binary representation of integers. I mean, if you're like into computer science, or basically, sort of write in a dictionary order. So 000, then 001, and then when you advance the units digit again, you carry, if you will, right? So then 010, then 011, and then 100, 101, 110, and 111. These are all 8 bit strings of length 3 that there are. I hope nobody came up with a ninth one. If you did, you have a repeat in your list somewhere. Um, some of you might prefer the approach of writing down all the bit strings that have no ones first, and then the bit strings that have one one, and then the bit strings that have two ones, and then the only bit string that has three ones. And I understand that general approach, but it starts to get haywire if the length of the string is more than 3. It's hard to keep track of. And I also actually should just note that at the very beginning of the semester, we had truth tables, and there was like truth table with a P column, a Q column, an R column, and TTT, TTF, right? Like so, there were 8 rows. They would sort of, in a sense, correspond to these 8. I know that maybe you might prefer to associate 1 with a T instead, but other than that sort of reversing, that should still hopefully work out overall. And just to make sure we're on the same page, I'd like to then ask how many bit strings of length 300 are there? And if we go based on our bit strings of length 3, and if the pattern continues, we would expect there to be 2 to the 300th power bit strings. This thing that we're actually experiencing here, I mean, obviously this is 2 times 2 times 2 times 2 times, and so on and so forth. If I scroll up just for a moment, it same deal here, right? This 2 to the third was a 2 times 2 times 2, and I started with 3 spots, 3 spaces, because I didn't want to start with 2 spaces. If we just dealt with 2 times 2, we'd have 4, and there's this coincidental problem of 2 times 2 and 2 plus 2 are the same number. So that's why I needed to start with 3. But I want to kind of go back to the strings of length 2 kind of situation to this is the warm-up idea to introduce what is called the product rule. Okay, so the product rule, not the product rule for derivatives. This is the product rule of accounting. It says that suppose a procedure can be broken into a sequence of two independent tasks. If there are n sub 1 ways to do the first task, and n sub 2 ways to do the second task, then there are n sub 1 times n sub 2 ways to do the procedure. So what we're seeing is an extended version of the product rule where you had 300 tasks instead of just two independent tasks. There were 300 independent tasks. We started with 3 independent tasks, but it's good to state that the version with 2 here. What's really happening here is this is the counting oh, sorry, I didn't see this question until just, oh yeah, that was 2 minutes ago. So the cardinality of the codomain to the power of the domain is the n cardinality. Yeah. Yes. So for functions, yeah, that's actually a good and that's an application of this product rule back to what we saw earlier. So let me answer that. Let me affirm quickly with an answer yes. Let me say one other thing about the product rule, and then I will get to a neat thing I wasn't going to talk about, but hey, why not? So what's going on here is this is actually the counting version of the explanation of if oh geez, there we go. If A and B are finite sets, and this matters, finite sets, then if you want to know A Cartesian B, remember this is the set of all ordered pairs, all possible ordered pairs, right? So the set of all ordered pairs, it sort of mimics very much the idea of you have to do the first task and you have to do the second task. Both tasks have to be done. So how many ordered pairs are there? What's the cardinality of the Cartesian product? It is the number of elements of A times the number of elements of B. So think of the elements of A as being the individual ways of doing the first task, and the elements of B as the ways to do the second task. Right? So that these to me, I mean, you've got to translate language back and forth between elements of sets and ordered pairs, which are elements of a Cartesian product. But these are two very different views of the same phenomenon. To go back and answer the question about this cardinality business, I will just mention this: if X, I wasn't going to say this, if X and Y are finite sets, again, finite is what's going to be key. Finite sets, the number of functions from X to Y is cardinality of the codomain. Let me write this here on its own line. The cardinality of the codomain raised to the power cardinality of the domain. In fact, I had made some brief mention, like when people stuck around at the end of the class the other day, related to some things about axiomatic set theory. When I took this axiomatic set theory course, the professor had actually, in that we're not going to use this notation, don't worry, but like just as an extra, I'll just comment that in that class we used this definition: if X and Y are sets, then let y to the x power, this notation be the set of all functions from x to y. And as soon as she wrote down this definition in class, like four hands raised up, and they're like, "Are Professor? I don't think you meant y to the x. Didn't you mean x to the y?" And she's like, "Nope, I meant y to the x." And people are like, "Are you sure?" And then immediately after, she wrote this, and said, "Hey, based on our definition, look, the cardinality of this set of all functions from x to y is cardinality of y raised to cardinality of x, isn't it?" And we were like, "Oh snap!" Right? That's yeah, that's awesome notation actually. So anyway, just a little side thing. I wasn't planning on mentioning it, but it sort of came up from the questions here. From the for the record, for the recording, the question was, so the cardinality of the codomain to the power of the cardinality of the domain is the n cardinality. Yeah. And that is, in a sense, actually an application of this product rule kind of happening multiple times, as many times as you have things in the domain of your set. Um, there is this other theorem. We're not going to prove it, but I mean, you can just sense this is true. If A and B are disjoint is key here, disjoint finite sets. Finite is also key. Everything we do in this chapter is finite sets. Then the cardinality of A union B is equal to the cardinality of A plus the cardinality of B. So this, just like earlier, I mentioned this brief theorem about the cardinality of a Cartesian product if the two factors are finite sets. This theorem leads to a counting rule. So this is a sum rule, and this says suppose a procedure, a larger procedure is done by picking exactly one of two tasks to do. Okay, if there are n sub 1 ways, to do the first procedure, or do the first task, I'll just stick to that word here. The procedure breaks down into tasks, two separate tasks, but you can only do exactly one of the two tasks. So if there are n sub 1 ways to do the first task and n sub 2 ways to do the second task, then there are n sub 1 plus n sub 2 ways to do the procedure. So as an example of how this applies, so let's say you're at a restaurant, and so with your entree at a restaurant, you get a choice of soup or salad. And let me clarify here, this or is not a mathematical or where you get both. That's going to require an upcharge. Okay, so soup or salad, but not both, right? If there are two soup choices for that day and three salad choices, how many ways are there to complete your meal? And in the end, then what you don't get to do both of the tasks. Like, so procedure is the word I'm using right now to mean like the big overall thing to do, but then there's a first task and a second task. And by first task here I mean picking a soup, and second task I mean picking a salad. You don't get to do both. You have to choose one or the other of those, and then if you go the soup route, then you get one of two choices. If you go the salad route, you get one of three choices. So in the end, an answer to this question should be 2 plus 3, not 2 times 3. That's the thing to clear up here. I'm going to end on one last thing, and then we will clear up some of what's going on next time. And there's a full version of this in the handbook. But if you ever go to Spain, there's this actually a lot of Spanish cities, you can fall into tourist traps where you pay 20 or 30 euros for a meal, and that's ridiculous. But there's this thing called Menú del Día, which for around 9 euros, you get a meal that's so for a fixed price, you often get a glass of wine with it and bread. And what you do then is there's like a section of the menu that says first plates, and you pick one of the first plates. So in the interest of time, I'm just going to write these as like maybe you have three choices, and for now I'll just call them plate A, plate B, plate C. And then there's second plates, and let's just to name these differently, D, E, F, G. Right. So what happens in this style of restaurant eating? It's a great, usually at lunch, it's way cheaper than the tourist traps, but you pick a first course and a second. It's a two-course meal for 9 euros. It's actually a really good deal, but you pick something from the first plates section and something from the second plate section. You're not allowed to pick two first plates or two second plates. You got to pick one from each. And so then how many possible combinations of meals can be made in total? There's a total of, this is multiplication here, right? Because both tasks have to be performed. This is 3 times 4 from the product rule. Versus over here, it was 2 plus 3 from the sum rule. And the main thing I want to sort out on Monday's class is when does the product rule really apply? When does the sum rule apply? So I think that's what I've got for the day. Again, please take a look at the homework. Homework 11 was just posted. So, and turn in homework 10 today. Question came in here. Could the chessboard theorem be proved by strong induction as well? Yeah. Sure, you could. I think it's a little harder to organize if you apply strong induction. In my opinion, I think here's the thing. I will say that when standard induction applies, it's usually cleaner. But yeah, in principle, yes. To answer your question just directly, yes, you could use strong induction. I think it's just much harder to organize the work because you'd be like taking these 3 other big squares and like cutting them into many, many pieces, I guess. So it could be done. It'd be a lot of notation. I will also say that if you can do standard induction instead of strong induction, it's preferable only because in standard induction, if you only need to use the previous domino, that's usually a cleaner argument because strong induction is sort of like, oh, the standard induction failed to work. I need more hypotheses, and so strong induction gives you these extra hypotheses. And if you use them, fine. But like, it turns out every time you can prove using standard induction, of course you can prove using strong induction because in strong induction you have the same hypothesis you would from standard induction plus additional hypotheses. So generally speaking, if quite literally, everything that can be proved by standard induction can always be proved by strong induction, though not the other way around. And so if you can do standard induction and the argument is clean enough, people tend to prefer that just because it means there's fewer things on the board than in strong induction. Does that sort of address it? But just to answer your question directly, yes, you could, but like it'll be a lot harder to write out, I think. Okay, I'll